Okay, so we've looked at determining a titration curve for an acid-base reaction or titration with a strong acid, strong base. Now let's examine the titration of a weak acid with a strong base. Same type of concepts are going to apply, except that since we're dealing with weak acids, we're going to have to deal with Rice charts or the Henderson-Hausbach equation, depending on when it's appropriate to do which. So we are going to determine the pH at various points in the titration of 10 mils of 0.1 molar acetic acid. The Ka value is 1.8 times 10 to the -5 with 0.1 molar KOH. First, what is the initial pH? So initial pH means that I've got my analyte, or I've got my Erlenmeyer flask here, got my analyte inside, I've got my burette up here, I'm adding my titrant. But initially, before any titrant has been added, what is the pH of my analyte? My analyte is my acetic acid. Why? Because I'm titrating this with KOH, which implies that my acetic acid is my analyte. So I want to do my initial pH. Initial pH is my weak acid, HA, plus water, in equilibrium with A minus plus H3O plus. Again, you can also write this equation as HA in equilibrium with A minus plus H plus with the appropriate states, but that's if you don't include water. If you do include water, you have to write H3O plus. If you don't include water, you write H plus. I don't care which one you pick, but pick one. We're going to do an ice chart here because the only thing we have in solution is acetic acid. We need to do a Rice chart because we have a partial equilibrium here, or we have an equilibrium, which is a partial dissociation, and we don't know how much will dissociate. Initially, we have a 1 molar solution, 0.1 molar of HA. Water doesn't matter. We don't have any of our acetate, our conjugate base to start, and we assume the concentration of hydronium is approximately 0. The change, minus X on the reactant side, plus X on the product side, always. And at equilibrium, 0.100 minus X, X, and X. Set up your K expression. We've got X squared over 0.100. We're going to ignore that minus X right there because we know that this is really small, so it's insignificant. And we set this equal to our Ka value, 1.8 times 10 to the minus 5. Solve for X. We find X to be equal to 0.00134. But remember, X also equals my hydronium concentration. Now that I've got my hydronium concentration, I can take the negative log of that value, and I find my pH to be 2.87. So initially, my pH is 2.87. It's acidic, which I expect. It's not really acidic. I mean, it's 2.87 is, more acidic than it is neutral, but it's still a higher pH, which I expect for a weak acid. What is the pH at the equivalence point? Well, this is a tricky question. It's saying what's the pH at the equivalence point. What it's not telling you is that you need to know the volume needed at the equivalence point. So how much base was needed to actually reach the equivalence point? And by volume, I mean what volume of titrant? Is needed to reach the equivalence point. Acetic acid is a monoprotic acid. KOH can pull off 1 proton. So my balanced equation, CH3COOH plus KOH is going to give me potassium acetate plus water. Do not use M1V1 here. This is not a dilution reaction. You must use stoichiometry. What I'm trying to find is the volume of NaOH. I've got 0.1 molar of my acid, and I have 10 mils of it that I'm titrating. Based on my balanced equation, I know this is a 1-to-1 mole ratio, 1 mole of KOH to 1 mole of acid. I know that my KOH has a concentration of 0.1 molar. Therefore, it takes 0.0100 liters. One too many zeros there. Or 10 milliliters to reach the equivalence point. We do have to do a BCA table because we have an acid reacting with a base. So our acid reacts with our base to form conjugate base and water. And this is a BCA mole table. So we do have to figure out the number of moles we have. For acid, I have 0.100 moles per 1 liter times 0.010 liters is 0.00100 moles, or 1 times 10 to the minus third. At the equivalence point, the moles of acid equal the moles of base. That's how I was able to figure out the volume. And I don't have any A minus to start, and water doesn't matter. The change, minus 1.00 times 10 to the minus third moles, minus 1.00 times 10 to the minus third moles, and plus 1.00 times 10 to the minus third moles. Students really get messed up on this minus and plus thing. It's always subtracted from the reactant side, added to the product side. The Ka or Kb will take care of the math ratio for you, but always subtract from the reactant side, add on the product side. After this neutralization reaction, I don't have any acid or base left, but I do have some conjugate base left that's been produced. I need to know the concentration of my conjugate base at equilibrium, or at the equivalence point. We're going to figure out equilibrium in a sec, but at the equivalence point, I have 1.00 times 10 to the minus third moles. And in total, I have 20 milliliters of solution, or 0.0200 liters, because I mixed that 10 mils of acid with that 10 mils of base, giving me an overall concentration of 0.0500 molar A minus at the equivalence point. Now I can go ahead and set up my my rice chart or my ice chart. You have to do that expression because now we've got a conjugate base, that's all that's present in solution, that will react with water. So all that's left again is the conjugate base, so that's going to be my reactant side. Conjugate base is going to react with water to form some of my weak acid and hydroxide. I have 0.0500 molar of the A minus. Water doesn't matter. I don't have any HA because I've reacted at all. I have to make a little bit more. And I have approximately no hydroxide at equilibrium, or at the initially. Initial, minus x plus x plus x. Again, always subtract on the reactant side, add on the product side. And at equilibrium, I have 0.0500 minus x, x, and x. Now, I'm running out of space all over the place. One of the tricks to this one is to recognize that you need Kb. How do I know I need Kb? I know I need Kb because I have hydroxide on this side. If I was to write the K expression here, K would be equal to HA times OH minus divided by A minus. Because hydroxide is in my numerator, I need Kb. I have Ka. I know that Ka times Kb is equal to Kw. Kw divided by Kb equals Ka. And Kw divided by Ka, that's what I meant to write, is equal to Kb. 1.00 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5th gives me 5.6 times 10 to the minus 10. So my Kb expression is equal to 5.6 times 10 to the minus 10. Let me shrink this down. So I've got 5.6 times 10 to the minus 10, and this is equal to x squared over 0.0500. Solve for x. X equals 5.27 times 10 to the minus 6th. That is equal to my hydroxide concentration. My pOH here, 5.28, and therefore my pH, 8.72. Now, one way to check yourself on this is to think about what pH makes sense. In this situation, I had started with a weak acid. I added strong base to it until it all neutralized away, which means I don't have any acid left, none of my weak acid left, at least from the initial weak acid. I don't have any strong base left, but I still see a basic pH. Remember, the weak acid reacts to form conjugate base. That conjugate base is what's causing that pH to be higher than 7 in solution. So if you titrate a weak acid with a strong base, forgot to lock the screen. If you titrate a weak acid with a strong base, you absolutely expect that final pH to be basic. At the equivalence point, I mean. What about after the addition of 2.5 mils of titrant? So you've got HA, your weak acid, plus OH minus, giving you conjugate base plus water. How do I know when to do a BCA versus a Rice chart? BCA is when I have an acid reacting with a base that it's not its conjugate, or a base reacting with an acid that is not its conjugate. In this case, I've got acetic acid reacting with KOH. Those are not conjugates of each other. They're not just throwing one proton back and forth. That's what conjugate means, is their difference of one proton. These are not a difference of one proton. Therefore, they will react with each other. Acids and bases will neutralize each other. And when that happens, you need a BCA chart. BCA charts are also known as mole tables because you must have moles to be able to do this. So this gives me 0.00100 moles, or this can be written as 1.00 times 10 to the minus third. And if I have 2.5 mils of the titrant, that's the same as 0.00250 liters times my 0.100 molar, 2.50 times 10 to the minus fourth moles of hydroxide. I don't have any A minus to start, and water doesn't matter. You always subtract the smaller of the two numbers here, so minus 2.50 times 10 to the minus fourth moles minus 2.50 times 10 to the minus 4th moles, and plus, because we are going to produce some of that conjugate base, 0.250 times 10 to the minus 4th moles. Do the calculation there and see what's left over. At the end of this neutralization, I still have 7.50 times 10 to the minus 4th moles of A minus. I don't have any of my strong base left, and I have now produced 2.50 times 10 to the minus 4th moles of my conjugate base. What I want you to recognize here, I have weak acid and conjugate base present, which means I have a buffer. You are welcome to plug this into a rice chart at this point and solve it that way. I choose not to. I choose to use Henderson-Hassbach because it's just faster. So Henderson-Hassbach, pH equals pKa plus the log of the concentration of base over the concentration of acid. pH equals negative log 1.8 times 10 to the minus 5th plus the log of my base. I have 2.50 times 10 to the minus 4th moles divided by, I've combined 10 mils and 2.5 mils, so 0.01250 liters of solution, divided by my acid, which is 7.50 times 10 to the minus 4th moles, divided by 0.01250 liters of solution. pH here, 4.26. So if I've added 2.5 mils of titrant, I've reached a pH of 4.26. What about the pH of the addition of 5 mils of titrant? Same process we just followed. My weak acid is going to react with my strong base, so I need a BCA chart. Remember, BCA means a single-headed arrow here. A minus and H2O are the products. I know initially I have 0.00100 or 1 times 10 to the negative third, whichever way you want to write that. Moles of HA. Again, that's found from these numbers here. We've calculated it a few times now, so I'm not going to calculate it again. And then if I have 5 mils of titrant, and the titrant has a 0.1 molar solution, I get 5 times 10 to the minus 4th moles of hydroxide. I don't have any of my A minus to start, and water is ignored because water is staying virtually constant throughout. Minus 5.00 times 10 to the minus 4th moles, minus 5.00 times 10 to the minus 4th moles, plus 5.00 times 10 to the minus 4th moles. Do the subtraction, and at the end you have 5.00 times 10 to the minus 4th moles of your weak acid, you have none of your base left, and you have 5.00 times 10 to the minus 4th moles of your conjugate base that you have now produced. And hopefully you recognize you again have a buffer, so we will again be using Henderson-Hassbach. pH is equal negative log 1.8 times 10 to the minus 5th plus the log of the concentration of base over acid. So 5.00 times 10 to the minus 4th moles divided by, in total I have 15 mils, 0.1500 liters. One too many zeros. There you go. Divided by 5.00 times 10 to the minus 4th moles over 0.0150 liters. pH here equal to 4.74. This is called your half equivalence point. At that point, pH equals pKa, and the number of moles of acid equal the number of moles of base. Basically, you've added enough titrant at this point to react or neutralize half of the acid, and half of that conjugate base has now been produced. What about the pH of the addition of 9 mils of titrant? 9 mils is right before the equivalence point. So 9 mils, same as 0.0900. I forgot a 0 in there. 0.0900 liters times 0.100 molar KOH equals 9.00 times 10 to the minus 4th moles of OH minus. Again, we need a BCA chart because we do have a weak acid reacting with a base. Single-headed arrow, A minus plus H2O. We know initially we have 1 times 10 to the minus 3rd moles of HA, and we just calculated that we have 9 times 10 to the minus 4th moles of OH minus. We don't have any A minus to start, and water does not change much, so we don't factor it into our equations. Minus 9 times 10 to the minus 4th, minus 9 times 10 to the minus 4th, plus 9 times 10 to the minus 4th. After this reaction, I have left 1.0. Notice this 1.0 here. That is for sig figs, so it is actually going down to 1.0 there. Times 10 to the minus 4th. No base, and 9.00 times 10 to the minus 4th moles of my conjugate base produced. Again, I have weak acid and its conjugate base present, which means I have a buffered solution. And I'm going to use Henderson-Hasselbalch. So pH, negative log of the pKa, plus the log, concentration of base. Total, we've mixed 19 milliliters, so 0.0190 liters. Divided by acid, 1.0 times 10 to the minus 4th over 0.0190 liters. I have had students ask me, when is it appropriate to use Henderson-Hasselbalch? They do not need to be the same volume of, or same number of moles of acid and its conjugate base, but they must both be present. If they're both present, it is appropriate to use. pH here, 5.69. And we're almost done. One more, and then we can go ahead and just summarize our findings. What is the pH after the addition of 11 mils of titrant? So at 11 mils, that's the same as 0.01100 liters times 0.100 molar, 1.10 times 10 to the minus 3rd moles of KOH. Our weak acid reacts with our strong base. Again, it doesn't matter if they're weak and strong. It matters it's acid and base reaction, and they're not conjugates of one another. But just to reiterate which ones you're looking at here. And now I have 1.10 times 10 to the minus 3rd moles of OH minus. I don't have any A minus to start, and water does not factor in. Note, we're very used to subtracting the concentration from the hydroxide, but this time the HA concentration is actually a little bit, or the number of moles of HA is actually smaller. So we're going to subtract that. And plus 1.00 times 10 to the minus third moles. After the neutralization reaction, I don't have any weak acid left. I have 1 times 10 to the minus fourth mole of strong base and 1 times 10 to the minus third moles of my weak acid. So here I've got a mixture of strong base and weak base. How do I find pH? Well, here's the trick. Your strong base will control the pH of the system. To understand this, I want you to think about what your conjugate does in solution. That conjugate base normally would react with water, forming equilibrium, make some of its weak acid and hydroxide in solution, right? Except that I've got strong base, so I'm adding a ton of hydroxide to the solution. Based on Le Chatelier's principle, or the common ion effect, what happens if I increase the concentration of this product? If this system's at equilibrium and I increase this concentration, Le Chatelier's principle tells me it's going to revert back towards the reactant side. That hydroxide is going to react with some of that HA that's produced, forming A-. It's called a common ion effect. Basically, the other way to think about this, and this is if I actually was able to create any, I'm not even able to create any. The A- reacts with water to form some HA and some OH- in solution, except that I already have a large concentration of hydroxide in solution just from the sodium hydroxide. So none of that A-, or if any, very, very little of that A- will react with water to produce any HA and OH- because there's so much hydroxide already present in solution. Remember, weak bases want to take protons, but they'll take them sometimes, and other times they'll give them back. Strong bases always want the protons. So the pH of this entire system is actually controlled by that strong base. Very, very little, if any, of this A- is going to be able to take any protons because those strong bases are picking up all the protons in solution. So this actually makes the pH calculation of this solution a lot simpler. All we need to find is the concentration of hydroxide we have in solution based on that strong base. We have 1.0 times 10 to the minus fourth moles of strong base left, and in total, at this point, we have combined 10 mils of acid and 11 moles of base, a total of 21 mils of solution, which is 0.0210 liters of solution. This gives me 4.7, sig figs here, 6 times 10 to the minus third. Again, 2 sig figs here. Calculate POH. POH is 2.32, and my pH is 11.68. So very, very basic pH. Now let's summarize our findings. So if we titrate a weak acid with a strong base, again, this graph is just general representation of it. It's not exactly the same numbers we have because we didn't do the exact calculations on this slide. But for the system we did have, at 0 mils, I saw a pH of 2.87. So this was just HA. At 2.5 mils, I had 4.26. At 5 mils, I had 4.74. This is my half equivalence, where pH equals pKa. At 9 mils, 5.69. At 10 mils, 8.72. This is my equivalence point. And at 11 mils, 11.68. Again, this graph isn't identical to what we did because the graph is using a different concentration of stuff. But what you can see is like your equivalence point here. Definitely basic pH. The equivalence point in this graph is at 12.5 mils, which means that our half equivalence point is about 12.5 mils. It's literally the halfway point to that. Our buffer region or buffer range is plus or minus 1 from the pKa range. All of that can be found from your titration curve. So when you want to find like equivalence point, the equivalence point is that point halfway up this large steep curve. Again, this happened at 25 mils. At 12.5 mils, that's my half equivalence, which is where pH equals pKa. And plus minus 1 to pKa to plus 1 is my buffer region for that acid specifically. So that's how you can find what buffer region you want if you're using a weak acid and its conjugate base or a weak base and its conjugate acid.